Assalamu alaikum, dear students. We're back with another video lesson, and hopefully this lesson is going to be the last lesson in chapter 1. Today's lesson will talk about gravitational force. Remember, gravitational force exists between any two objects because of their masses, and we know that gravitational force is a field force. That means no matter how many barriers you put in between two objects, they will always attract one another because of their masses. So if that is the case, how can we define gravitational force? We can say gravitational force, it is a mutual force of attraction because of, or let's say between any two objects here, or you can say because of the particles of the matter, regardless to the mediums that they are. So gravitational force, once again, it is the force of attraction between any two objects, we can say because of their masses, no matter big or small. But of course, the bigger the masses, the greater the effect of this gravitational force, we can say. All right, so that'll be, so remember this, we said gravitational force is a field force that experiences between any two objects. So this is how we can define them here. And then, for example, gravitational force between the Earth and the Moon, of course. And by the way, this gravitational force, of course, between the two, it is equal in magnitude and opposite in direction here. Okay, so how do we, calculate the gravitational force? But before that, let's talk about this did you know thing here. Basically, this piece of information, you can say it is not included, but it has the name of a scientist. We need the name, of course, to answer one of the, let's say, standardized test preparation questions here. What does it say? And of course, it says Kepler suggested that planets revolve around the sun in an elliptic, you can say. So we know that, or sometimes when we draw, let's say, the orbit of a planet that is revolving around the sun, sometimes we do a perfect circle. But Kepler suggested that this orbital, let's say, or this orbit is not a perfect sphere, it is rather an elliptic, you can say. So what do we mean by an elliptic? You can say it is more like an egg shape at that point here. So if that is the case, you could say this is a perfect sphere. That is not how the orbit of a planet looks like. It rather looks like something like this one at this point here. And this is what it is. So for example, this is the Earth, let's say, traveling around the sun at this point here, or you can say orbiting, revolving around the sun. So once again, who suggested or who found out about this one? It was a scientist. His name was Kepler. And even though, of course, scientists, like previously, they used to believe that Earth was at the center of the universe, let's say, and every other things were revolving around the Earth. So scientists continued to believe in that, let's say. They didn't believe in Kepler, let's say, until, let's say, Sir Isaac Newton was able to drive the elliptical path suggested by Kepler using his law of, we can say, of motion here. Okay, now, so now we have something, of course, it is called the Newton's law of universal gravitation. This is one of the most important laws that we have. What does it say? Because it is basically is about the law of gravity, you can say. So it says that every mass, or every, let's say, mass in the universe, it attracts as, let's say, every other mass in the universe with a force that is directly proportional to the product of their masses, and inversely with the square of the distance between the two. Let me tell you what exactly Newton stated here. He said that if we have two masses in the universe, no matter how small or big they are, okay, so let's call them M1 and M2 here. He said that the force of attraction between these two masses, of course, we call them gravitational force. He said it is directly proportional to the product of the two masses. And you know, what does the product means that means the multiplication, right? He said the gravitational force between the two is directly proportional to the product of the two masses and inversely with the square of the distance between the two. That is what he said. So of course he said that is basically how it looks like. So if we want to make this one an equation, of course, we need a constant. So now at this point we can say gravitational force that is equal to G. That is a constant, of course, you can say, and then that'll be equal to G times, we can say, M1, M2 divided by the distance between the two squared right at this point. We know that forces are measured in Newton, that is obvious, right? And this G here, remember, it is called a constant of universal gravitation. Don't forget, this has been in Wizari so many times here. So what is G equal to? it has a value. We're going to write the value, and also what is it equal to, or what is the unit of g? We can say g, it is equal to 6.67, you can add even 3 times 10 to the power negative 11. But what about the unit for g? If you want to know the unit of g, always, you don't have to memorize the unit. If you know the equation, make g the subject, the constant for universal gravitation. If you make this one the subject, that'll be fg times the distance squared divided by m1 times m2 here. So once again, now at this point, we can say the unit will be what? The unit of force is Newton. The unit of distance, that is in meter, but because it is squared, we'll say meter squared. And the unit of this mass is kilogram, and this is kilogram. Kilogram times kilogram, that'll be kilogram squared, and that is the unit for, you can say, constant of universal gravitation here. So remember both the magnitude, most of the time the magnitude will be given, but you need to know, just in case if it is not given in Wazari, and of course you can memorize it very easily, that'll be the magnitude, and this will be the unit for g, remember. Okay, and these are the masses of the two objects here. This is the distance between the two. Let's say this is the distance that separates the two. Okay, so whatever the force of gravity is, all right, let's just say 10 Newton, for example, here. So if this, for example, mass is attracting, let's say this mass with a force of 10 Newton, then of course this mass would be attracting the other mass with another 10 Newton. But of course these forces will be equal in magnitude and opposite in direction. So once again, that is the law of, or you can say what Newton stated regarding the gravitational law. He said that, let's just make it simple. We'll say that the gravitational force between any two masses, it is directly proportional to the product of the two masses and inversely proportional with the square of the distance between the two masses. That is basically what he suggested, or what he said. Okay, now going back to this one. So that is, remember these red stars means these are been in Wazari recently here. Okay, now we have few study tips, and you need to remember those here. The first one says gravitational force that is directly proportional to the what? To the product of the two masses, which we just said it, and of course inversely proportional to the square of the distance between the two. Now we can rewrite the equation this way too. We can say gravitational force that is directly proportional to the two masses, m1 and m2, and inversely proportional with the square of the distance between the two masses as well. Now we have another point. The second point says what? Kepler suggested that Earth has an elliptical path, and Newton proved that using the law of, you can say the laws of motion here. Now, for point number 3, we have two equations here. One of these equations are not included actually for you. It is cancelled here, and that is, you could say, the orbital equation, or the orbital period. Okay, but what does it say? Orbital speed and period can be found using Kepler's third law of motion here. So this is, you can say, the orbital speed, okay? And this would be the orbital period. But this one, it is cancelled, so you don't need about this one. But where does this equation come from? Okay, let me tell you where this is coming from here. Now, we've mentioned previously, like in the previous section, we said that if, let's say, an object, or let's say Earth, if it is traveling or moving around, let's say, the sun here, that is clearly what force provides this centripetal force? That is, gravitational force provides what? Provides centripetal force. Is that true? So in that case, of course, we can say Fg, it becomes the Fc. If that is the case, Fg becomes Fc here. Now, but what is Fg? I think, all right, I'll still do it here. Fg, we just said it, that it is equal to what? Fg here, it is equal to gravitational universal, or constant of universal gravitation, times m1 times m2, let's say, divided by what? Divided by r squared. On the other side here, we have Fc, which is basically the centripetal force here. What is the centripetal force equal to? It is equal to mass times tangential speed squared divided by the radius. Now we can say the mass, one mass cancels out with one mass here. That would be the mass of a smaller object, you could say. And then what else is, for example, what about this 1r cancels out 1r here? So if you want to find the orbital speed, we want tangential at that point. If you make tangential the subject here, what would you get as a result of this? So tangential squared, it is equal to what is left on this side, because these two both cancel out. That would be g times mass is one of the masses, that is clearly the mass of a bigger object here, divided by the radius. So we'll say g, the constant of universal gravitation, times the one of the masses, can I just write m capital for the bigger mass, and that'll be the mass of a planet, divide by the radius of the planet, they'll just make it r capital. But we want tangential speed, or let's say orbital speed in that case here, so we'll just take the radical or square root for both sides. In this case, v tangential, that is equal to what? It is equal to the square root of, or the radical of g capital, m capital over the radius here. So this is where this equation comes from. Tangential or orbital speed, you could say it is the square root of g, that is the constant of universal gravitation, times the mass of the planet divided by the radius of the planet. So based on this equation, you can see that the orbital speed does not depend on the mass of the object, it rather depends on the mass of the planet and the radius of the planet only. Okay, and of course the universal constant too here, gravitational constant. So basically we have another question says, what does the gravitational force depends on? Whenever there is a question says, what does this thing depends on? If it has an equation, write it down. So basically it depends on everything that is written in the equation. If you have constants, of course we don't mention the constants because constants are not a variable at this point here. So we can say, if what is gravitational force depends on, we can say it depends on the two masses or the product of the two masses, which is directly proportional. How do we know if something is direct or, let's say, inverse? Let's say you have a fraction, it could be anything. If it is something, for example, whatever, if it is something above the fraction here, you can call it direct, okay? Anything, for example, it is above a fraction, you can call it direct. And if it is below the fraction, for example, it is called inverse here. So what if, for example, we have two things that are beside one another, let's say, or it could be anything. Let's just say F equal to mass times acceleration here. We want to know, for example, the relation between mass and acceleration. Whatever that you want to know, for example, how, like you want to know the relation between two things, always make one of them the subject. Let's say we want to know the relation between mass and acceleration here. Even if there's no fraction, you can write one under, let's say here. So let's just say we want to find the relation between mass and acceleration. In that case, of course, acceleration becomes F over, let's say, the force over what? The force over the mass. So now we can see that anything above the fraction with this, that is going to be direct, and anything below is inverse. So now we know that these two are directly proportional, but these two are inversely proportional. And if you want to write them alone here, that would be 1 over the m. So this is basically inversely proportional. I hope you already know this one, but just in case, Yanni, if you were not sure, of course, you can benefit from that note there. Okay, so now we can see that it's directly proportional to the product of the two masses, direct. And inversely with the square, don't forget, you cannot just say the distance, Basha. It has to be the square inversely with the square of the distance between the two. Now we have a question, you could say, says use Newton's law of universal gravitation to determine the gravitational acceleration of free fall, but on Earth, don't forget. Okay, that means, all right, we're going to use, let's say, the masses on Earth, and of course, one of the masses is going to be on Earth. Remember, gravitational, let's say, acceleration of free fall, that is basically Fg on Earth, you could say, and then that is going to be, you know, like it is equal to what? It is equal to G. Let's say m1 and m, let's say, you know, like that would be the mass of one of the objects here. This would be the mass of the Earth at this point divided by the distance squared between the two objects. But we know that Fg, it is equal to what? We know that Fg, it is equal to mg, right? Okay, if that is the case, then that is g again, m1 we could say, or you could just say m, and m capital, that would be the mass of the Earth, and then divide by the let's say the distance between the two. But we know that the distance between the two, that would be the radius of the Earth. Imagine if an object is, let's say, on the surface of the Earth, that would be m1, and then the other object would be the mass of the Earth, right? And of course, the distance between the center of gravity is right at the center, so the distance is going to be the radius of the Earth at this point here. So can we cancel out one of the masses here? Yeah, so we can see that gravitational freefall acceleration on Earth, that is equal to g, that is the constant for universal gravitation, times the mass of the Earth, and then divided by the radius, you could say, or the distance between the two. As you can see here, at this point here, or you could just, yeah, you could say the radius here. At this point, you can see that the gravitational, or you can say the free gravitational, let's say, acceleration of free fall does not depend on the mass of the object. This is why when different objects fall, if we disregard air resistance, they will always fall with the same speed, you could say, because they will always have the same gravitational acceleration. Or you can say, let's say in free fall, right, all objects, regardless to their shapes, will always have the same gravitational acceleration. And of course, because the surface of the Earth is not, let's say, it is not, like the same, like everywhere, because we have some places, let's say, if we just think of, for example, an example, there are ups and downs at the top of a mountain, then there could be a valley, let's say, or a well. Some places are closer to the center than other places. So some places, let's say G, of course, is going to be bigger or higher, right? And some other places, if the distance is larger, of course, G is going to decrease. But in order to take an average value, of course, we're just going to take an average, or we'll use 9.81 as an average value between the, let's say, the smallest and the biggest here. So let's get back to the question. All right, the question says what? Find what? Says find, or let's say determine the gravitational acceleration of free fall on Earth. We were just saying that, right? G on Earth, all right? That was the question that we got. Let's say constant of gravitational or universal gravitation times the mass of the Earth divided by the radius squared of the Earth. So now all you have to do is just plug in the numbers for G. 6.673 times 10 to the power negative 11 times the mass of the Earth that is given, which is 5.98 times 10 to the power, okay, that is 24 kilograms, and then divided by the radius of the Earth, which is 6.73. But I'll tell you a trick regarding this one. You have to be really careful at this point. Times 10 to the power 6. Now, just because you're writing this power 6 subconsciously, you might feel you've wrote the power. So what is the best method not to forget this square that we have in here? Always draw the bracket first, square it, and then whatever the number is just fill in the bracket. This way, hopefully, you will never make any mistakes. Because I sometimes accidentally, because of this power 6 you write, or whatever the power that you write, you think subconsciously that you already wrote the power while you didn't. So make sure you write the bracket squared first, and then whatever the number is, you just fill in that case. So once you do this, of course, you will get something, or G, the value for G, is something about 9.83. See, this is not the number that we use, but of course, this is one of them. That is meter per second squared at this point here. Once again, we said for gravitational free fall acceleration, we'll use an average value, which is 9.81, because it ranges from 9.81 to 9.83, or you can say it ranges actually from 9.78 to 9.8378 to let's say 0.83. So we'll take an average, which is going to be 9.81 here. Okay, now here's another question, which is you also need to be aware of. It says, why the law of universal gravitation is considered as an example of an inverse square law? I think it is pretty obvious from its name, because the force of gravity changes inversely with the square of the distance, and that's it. Okay, so think about how the relation between force and the distance, are they inversely proportional? Yes, that is the first part. Is it just with the distance or with the distance squared? Well, then it's with the distance squared. This is why we say it is inverse square law, all right? Because the force varies as the inverse square law of the separation. That is, the force between two masses decreases as the masses move further apart. Clearly, if the masses get closer, all right, the force of attraction gets stronger, and if they move further, the force of attraction gets weaker. But how? By an inverse square. Don't forget that. We're gonna, give some examples at the end, see how the changes happen between, like for example, if the mass get closer or further. All right, but first, let's solve a few questions maybe. It says what? Find the distance between a 0.3 kilogram billiard ball and a 0.4 kilogram billiard ball if the magnitude of the gravitational force between the two, or between them, is 8 times or 8.92 times 10 to the power negative 11. So how do we solve this question here? That's pretty easy, actually. Okay, so let's keep this one here. All right. So once again, it says what? One of the masses, let's just write down what is given. One of the masses is 0.3 kilogram. the other mass is 0.4 kilogram. And then it says the gravitational force between the two. So we can say Fg, it is 8.92 times 10 to the power negative 11 Newton. That is as simple as this. What is the requirement? It says find the distance. All right, so here's the distance. That means find r between the two. Now we know that gravitational force at this point, just make this one here, gravitational force Fg, it is equal to G m1 m2 divided by r squared at this point. So we want r. Can I just swap this to here? So we can say r squared, it is equal to gravitational or constant of universal constant, gravitational constant, m1, m2 divided by Fg. We want r, not r squared. So can I take the square root for this one? Yeah, so let's just do that here. So we'll just make this one squared. And then, of course, we'll remove this one here. So we can, at this point, we could just write the numbers in. So we'll say r, it is equal to, once again, the radical of g, which is, let's hope I have left enough space, let's say. We said the g value here, that is 6.7673 times 10 to the power negative 11 times the first mass, which is 0.3, times the second mass, which is 0.4, divided by Fg, which is 8.92 times 10 to the power negative 11. All right, so I would recommend you do the numbers, for example, the first one, then divide by the second one, then whatever the answer is, then take the radical of the answer. Using your calculator, you can find the distance between the two. And I think it is 3 times 10 to the power negative 1, which is the same as 0.3 meter, you could say. That is the distance between the two. Let's double check the answer. Yes, it is. And that is how you could do that very easily. That is the first question that we have. Okay, let's move on to the next one. Okay, now what is the next question? We have a practice. It says if the masses of each ball in sample problem 11 is 0.8 now, at what distance between the balls will the gravitational force between the balls have the same magnitude as before, let's say. So now we had, let's say, the same magnitude. That means in order for Fg to stay the same, if the masses get larger, right? Remember, we said that if you increase the mass, gravitational force increases as well. But the question says, what if the gravitational force is the same, okay? And the mass got larger here. In order to keep the same force, we'll have to move the masses further apart to keep the same gravitational force. So how far should the two masses be in order to keep the same force at this point here? So we're just going to do this one too. Okay, so once again, we want the radius again at this time here. So the same thing we could say, that is going to be the radical of g times m1 times m2 divided by Fg here. So at what distance should, should they be, so that, remember, to keep the same forces here. At this point, there is a force here. If the mass get larger, they'll have to get further apart so that we can, let's say, keep the same gravitational force between the two. All right, so here at this point, g again, 6.673 times 10 to the power negative 11 times the first, each mass is 0.8 now, times 0.8, right? And then the force between the two were, I think it was 8 point something. Let's see if we can get that one here. What was it? It was 8.92 times 10 to the power 11. 8.92 times 10 to the power negative 11 here. So now if you want to find the distance now, of course, it's going to be what? It's going to be, let's just keep this one here. The distance is going to be 0.692. R is going to be 0.692 here. Do you remember the previous answer? The other answer was R was 0.3. So if you want to keep the same gravitational force and increasing the masses, of course, they need to get further apart to basically keep the same gravitational force between the two. So that'll be the answer at this point here. All right. Now, let's talk about something else, which is very important at this point here. Okay, now, remember this says if there are two forces and two radii, and one of them is unknown, you may use this equation here. So let me tell you a little about this equation here, or how do you use this one here. So imagine you have, let's say, we have two masses at this point, okay? So these two masses, each one of them has a certain mass, let's say. Okay, M1 and M2, let's say. And then, of course, there is a certain distance between the two, you could say. And of course, now we have a certain force, let's say, between the two here. What happens if we move the masses, let's say, further apart? Or we could even bring them closer here. Now, by moving them further apart or closer, of course, now the force is going to change and the distance is going to change. So we'll say, to make it easier here, we can say if you're given two forces and two radiuses, all right, then we can use this equation here. So we can say, let me write it down here. We can use this equation. We can say F2 over F1, that is equal to what? It is equal to R1 squared over R2 squared. This is the equation that you need. Keep that in mind. But where does this come from? Of course, it comes from the simplifying of each one of these equations. F2 over F1, which is equal to what? F2, clearly it is equal to G, M1, M2 over R2 squared, and then divided by G, M1, M2 over R1 squared here. So these are, like same values here. We just, like cancel them out. That'll be 1 over R2, and then here would be 1 over R1. But we take the reciprocal of this. So these are squares. I wrote them. Okay, so we take the reciprocal of this one. The first one is going to be 1 over R2 squared times the other one is going to be R1 squared over 1. So in this case, of course, you just combine them here. And then you will get this equation right here. Okay, I don't have to write the last step here. So this is what you get. Now, I need you to remember at this point, you have 3 things to do. Now, remember this. If the question is about gravitational force, you have this equation. Gravitational force that is equal to G, M1, M2 over R squared. That is one thing you need to do. If you're given masses and distances, masses and force, the distance is unknown, you can use this equation. And then if, let's say, the equation or the question is only for example, the force, the relation between force and distance, then this is the equation that you're supposed to use. For example, if it says, now, let's say, what happened to the gravitational force between two masses if you increase the distance by this much or decrease the distance by this much? Now, that would be one distance, all right? Changing one distance, so you can use this, this equation or this relation here. But if you're given, for example, two forces and two radiuses, only one of them is unknown, then you can use that equation, which is F2 over F1. It is equal to R1 squared over R2 squared. How not to forget this? Remember, these two are F1, R1, and these two are F2, R2. Remember this one. That might help you, for example, to remember them better. Now, after we know this, now let's see if we can solve a question. Remember, that is the equation you need to know. Let's see how we can use this in calculations. First of all, we have Uzadi question here, okay? What is the Uzadi question saying? Watch this one closely. Let's clean this a little bit, maybe. Okay. It says, two small masses which are 10 centimeter apart. I believe we need this one too. So let's bring this one to here. It says two masses which are 10 centimeter apart. Okay, let's clean this one here. We have two masses that are 10 centimeter apart. Remember this. Okay, so can I call this one the first radius 10 centimeter apart? Then it says attract each other with a gravitational force of this much. So can I call F1 here? So 10 times 10 to the power negative 11. You might say, how do I know it is R1? This is the first distance where they are. They're 10 centimeter apart, right? And then there is a force that they attract each other with this much here. So you can call it F1, and this would be R1. Next, watch this closely. It says, if they are moved to a distance of 5 centimeter. So now these two masses are moved closer, right? So this distance is going to be 5 centimeter now. So it is this distance, or can I call this distance the second distance here, which is 5 centimeter? And then it says, how much force will they exert on each other now? But before we answer the question, did the two masses get closer or further? Closer. So the force of gravity or gravitational force must get larger than the first time. If it is not greater, the value that you find, then double check your work. Maybe you've done something wrong. Okay, so now F2 is unknown. So remember we said if you're given two forces and two radiuses or distances, then this is which equation do you have to use? We're going to use this equation here. We said, let's just do this one here. F2 over F1. We said how to remember. Each one of these has to be, like opposite to one another on the same line. So R1 squared over R2 squared. Now all you have to do, just plug in the numbers and you can find the answer. So one more time, F2 is unknown, that is required. F1, that is 10 times 10 to the power negative 11, it is equal to. Now regarding the radiuses, okay, because we have radius both up and down, it is totally fine if you keep them in centimeters. Why? Because they cancel out. Okay, so if that is the case here, we could just say, for example, you can even actually convert it to meter. That would be 0.1 meter if you want to. This is going to be 0.05 meter. So whether you write these numbers or convert them to meter, it is exactly the same. Why? Because we have both, let's say, distances on top of one another, so the units will cancel out. So I'll just keep the same unit here. That is 10 squared over 5 squared. Now the easiest way is to calculate this part. Whatever it is equal to, then just multiply by this much, you cross multiply. So F2, in that case, of course, it is equal to whatever is this one here, and then just multiply by 10 to the, let's say 10 times 10 to the power negative 11, then you will find the answer. Whatever the answer is, then of course you could just see which one is correct, and then of course you can make the right choice or choose the correct answer at that point. All right, that is regarding this question right here. I think, by the way, let me just get back this one. The answer that you get here, the answer that you get in your calculator is going to be 4 times 10 to the power negative 10. Be careful. Right, now you might not see this one here, but we have an answer here that is written 40 times. Can I make, for example, add 1 0 here and then make, for example, the negative power here 1 extra? It is negative 10. If I add a 0 here, that is going to be negative 11 here. Don't forget, this 1 0 cancels out with 1 here, so that you still get the same answer, of course, which is 4 times 10 to the power negative 10 here. So this will be the correct answer at this point here. Okay, now let's talk about something else. It says find the magnitude of the gravitational force on a 67.5 kilogram person that would experience while standing on the surface of each of the following planets here. So there's a person, once he's on the surface of the Earth. I think I should go back to the other one. Once he is on the surface of the Earth, okay, what gravitational force would be on him? And then second time he will go to the surface of the Mars. What will be the gravitational force on him once he's on the surface of Mars? So let's do this one too. Okay. Let's make this one bigger here. We need these numbers here, so remember this. The first mass that we have, it says the mass of a person. You can call it M1, or you can even write small m for the mass of a person, which is 60, what was it? To roll down a little bit, it is 67.5. 67.5, that is kilogram, mass of the person. And then let's say the mass of the Earth, that would be what? That is 5.98 times 10 to the power 24 kilogram. And of course, we have the radius of the Earth, which is going to be 6.37 times 10 to the power 6 in here. Okay, so now how do you find the gravitational force on the person? We know that Fg, gravitational force, it is equal to what? Constant of universal gravitation times mass of the person, mass of the planet, and then divide by the radius of the planet squared. Okay, once again, that is 6.673 times 10 to the power negative 11 times the mass of a person, right, times the mass of the Earth, which is, again, 5.98 times 10 to the power 24, and then divided by the radius or the distance squared. Once again, remember, so always write the power or the bracket squared, then whatever the radius is, just squared. The radius is going to be 6.37 times 10 to the power 6, so that you don't make any mistakes here. Now just do the math, you'll find the answer. The gravitational force on a person, that is going to be 664 Newton. That is it. Now, you copy the same exact thing on the surface of the Mars. This time you're going to use the mass of the Mars the radius of the Mars. And of course, you do the calculation and you will get the answer right, inshallah. Okay, let's erase this. All right, so what else do we have next? Let's just move this one here. We have a question that says, comment on the statement, there is no gravity in outer space. What do you think about this? Is it true, or can we say it is true there is no gravity in outer space or at the edge of the universe? The answer is no. We said gravitational force exists between any two objects because of their masses, no matter how far. But clearly, the further they are, the weaker the force of gravity. But we can never say there is no force of gravity, no matter where. Okay? All right, now remember these questions I told you these were Bin Wazari. It says, what is G here? It is a form of, you can say, of universal law of gravitation. Which of the following formulas are used to find G? Just make G the subject. Isn't it G, for example, this one here, Fg times distance squared divided by mass 1, mass 2? That'll be it, right? And of course, you could double check by yourself too. Just make G the subject, rearrange the equation. What about the value for G? We said, the value for G sometimes, it is recommended to memorize the value just in case if required for questions like this. We said 6.673 times 10 to the power negative 11 Newton meter squared, kilogram squared. Don't forget that one either. G in the equation F this much this, what is it called? We said constant of universal gravitation. Now this table here, what I like to explain and what do you need to pay attention at or for. It says the effect of changing the mass and the distance on the gravitational force between two objects here. So this is the equation that we have, and I need you to focus at this point just a little here at this point. All right, watch this. So the equation that we have, it is this much. So once again, we said Fg, it is equal to G capital, M1, M2, and that is the distance squared here. So the question says, what happens if I double one of the masses here? We know that the force is directly proportional to either masses, right? If I double one of the masses, that means make it 2 times. What do you think will happen to gravitational force? Will it be doubled? So we'll say gravitational force will be doubled. Well done, that is the correct answer. What if I double both masses here? So that means this is doubled and this is doubled. So what do you think, by what factor will the gravitational force change? Will it be 2 times 2? Will it be 4 times? Yes, so we can say the gravitational force will change by 4 times. So if you want to do this, you could say M1 and M2. So this is doubled and this is doubled. So Fg, of course, it will change by 4 times, you could say. Or it will just change by 4 times, you could say. All right, now, what if we double the radius or the distance, let's say? Watch this. We said that for this one, you have to be careful a little. We said that what is the relation between Fg with the distance here? Are they direct or inverse? They're inversely proportional. So if you double the distance, watch this. Remember, the distance is squared, yes? So if you double that, double squared, that means the gravitational force is going to change by a factor of 1/4. Now hear me out. I'll ask you the same question, but in a different way. I said if we double the distance, the gravitational force change by a factor of 1/4. But what if I say, if we double the distance, by what factor will the gravitational force decrease? In that case, you will just say 4 times. All right, remember this. If I say by what factor will it change, that is 1/4. But if I already say decrease, by what factor, let's say, will the gravitational force decrease? In that case, you don't say 1/4 again. No, you will just say 4. Because decrease already means 1 over something. How many times will it be less? That's what I'm saying. You just say 4 times less. So pay attention to that. Now the next one, what if we have the distance? That means make the distance half of the previous one. You will do the same thing, right? This time, right, it is going to, if we bring the masses closer. If we make it half, and it is squared, so what would be the answer to this one? It is going to be 1/4, and this 4, of course, goes up. We can say the gravitational force increases this time 4 times. Or you can say changes by a factor of 4 at this point. So be aware of these conversions here because, these are actually good questions, or you can say good question materials, actually. So remember this, that is what we have. It says doubling one of the mass, the force will be doubled. Doubling both mass, the force will increase by a factor of 4. Doubling the distance, the force will become 1/4, all right? Or decreases by 4 times, you could say. But if we have the distance, the force will increase by a factor of 4. Now remember the questions regarding force and distance. These are 2 more questions, of course. We can practice them just to see how we can do them. So let's practice this one more time as well. Okay, so here's what else do we have at this point? It says what? It says 2 objects with 2 specific masses and specified masses and specified distances separate them. If the distance between them becomes half the distance of the first time, by what factor the gravitational force between them change here? So since we could say, how about if I just use this equation here? Isn't it the question is about force and the distance, right? We'll just change the distance at this point here. It says if the distance between or become half, right? So if the distance become half, that is what we're going to write. So 1/2, but don't forget the squared. So it's going to be 1/4, yeah? The 4 goes up, so we can say the force increases by 4 times in here. So do we have this as a multiple choice? Yes, that is going to be option C at this point right here. All right, I'll have to bring the other one back so that we can write on it. Otherwise, we cannot. So let's just remove this one. So this is going to be the correct answer at this point here. Okay, now what about the next one here? It says, watch this. 2 objects with 2 specified masses and a specified distance separates them. If the distance between them increases by a factor of 5, so this time the distance increases, be careful with that. By what? By 5. What factor will the gravitational force between the 2 change? Once again, this time is going to increase, not decrease. So we said it is 1/r². So that is going to be 1/5. But don't forget, that is 1/5². So it is going to decrease by a factor of what? It is going to, it says, by what factor will the gravitational force between them change? In that case, it is going to be 1/25. That is the correct answer. All right, now we have 2 more questions which I would like to solve them for you here. Pay attention to them. The first one says, the universal law of gravitation or gravity between 2 objects is one of the examples of the inverse square law, yes? Inverse square law. Why is it that, right? What is the reason why? Let me just get rid of that tag here so that we can see the whole question. All right. So that is what it is. So once again, it says that because the force is directly proportional to the square of the distance between the 2. Is it direct or inverse with the distance? It is inverse, so this is incorrect. B says because the force is directly proportional to the inverse square distance between the 2 masses. Is it directly proportional to the inverse square distance between the 2 masses? We would say yes, okay, but let's just continue with the choices here. C says the force is inversely proportional to the product of the 2 masses. Is it inverse or direct with the 2 masses? So again, this one is incorrect. What about D? It's a bit tricky, D. By the way, it is incorrect though. It says what? The force is inversely proportional to the inverse square distance between the 2 masses. What does exactly this mean? Watch this. It says, let's just translate option D into an equation and see what it turns out. It says the first part says the force is inversely proportional. And we know that when it says inverse, that means 1/something, right? You agree with me? Well done. But it says inversely proportional to inverse square distance. That means another inverse square distance. Is that true? If that is the case, 1 over the distance square, so this distance goes up, it becomes the same as if you say it's directly proportional. Because the inverse of the inverse, it cancels the effect of the inverse, so it becomes directly proportional here. We know that this is incorrect. So now the only correct option that we're left with, of course, it is option B at this point. Now, question 7 is also a very good question, actually. I would like to do them here because there is a simple idea in that, which I believe you might already know them. I don't know why I came here, but let's get back to this one here. It says what? It says the distance, right? it says the distance between the center of two billiard balls of the same mass, all right, is this much. Remember this, when it says the same mass, that is a keyword for you to know. Okay, so the same mass. Let's just, explain this one here. So we have, let's just move this one a little bit. The other one is gone. I need to get it back. Should have pinned that one. Okay, so here says the distance. So there are, here we have two billiard balls, right? That says the same mass. So whatever the mass of this one is the same for the other one here. The distance between the two is 0.3 meter. That's what it says. If the magnitude of the gravitational force between the two is 9.05 times this much, right? So here's the gravitational force between the two. What is the mass of one of those balls? Be aware of this keyword here because it says, what is the mass of one of them here? So we're given, it says the same mass. When it says the same mass, be aware of that. So if you use the equation here, we say, of course, Fg, it is equal to G capital, the constant of universal gravitation, M1 and M2. But these are the same masses. We can make them M squared. Do you know that? M times M, because these two are the same. Can we just call it M squared? Yes, we could do that here. Okay, so divided by the distance squared between the two. Okay, so we said instead of these two masses, I can just write them squared here. So G capital, M capital, we could say. M squared, that is M squared divided by the distance between the two squared, yes? So we want the mass, so can you cross multiply? So you will get Fg times the distance squared, that is equal to G capital here times mass squared here. How do you get the mass back? So we'll say mass, just divide both sides by this or bring this one here. That'll be what? That'll be Fg times the radius squared divided by what? Divided by G. Do you agree so far? Very good. But remember, this is mass squared, yeah? So we want the mass of one of them. So how do you get the mass of one of them? Just take the square root for both sides. M would equal to, that'll be Fg between the two, times the radius between the two, and divide by the constant of universal gravitation. Now, all you have to do, just plug in the numbers at this point here. So once again, what is the gravitational force between the two? 9.05 times 10 to the power negative 11, multiplied by the distance between the two squared, that is 0.3 squared, and then divided by G, which is 6.673 times 10 to the power negative 11. So you do the math, of course, you will find the mass of one of the masses only. Just plug in the numbers, and of course you will find the answer to one of them. As a matter of fact, let me get a calculator, see which one of the answer is it at this point here. All right, so first, try to calculate what is inside the radical, the square root. That is going to be 9.05 times 10 to the power negative 11 times 0.3 squared. You can press equal at this point, then divided by, open a bracket for this, 6.673 times 10 to the power negative 11, and you can close the bracket. The answer is going to be 0.122, right? Now take the radical of the answer. The answer is going to be 0.349, which is about 0.35 kilogram for each mass. So we'll say 0.35 kilogram for each mass. That is going to be the answer. Do we have this in the choices? Yes. And that is going to be option B, right? 0.35 kilogram. And yes, that is option B, which is clearly this one. This is how you can do that. The reason I wanted to do that, sometimes instead of saying the same, the masses are the same, they say identical masses. So these are keywords for you to know them. Okay, now let's go through some of the section review questions here. One of them says, roller coaster moves through a vertical loop at a constant speed, suspend it is passengers. Do you remember that keyword? We said whenever it says suspends passengers upside down, that is inside, for example, the vertical loop in here. So these are the direction of each one of the forces that we have. In which direction is the force? So they're asking about the direction, the force that causes the coaster and its passengers to move in a circle. So the forces that cause the passengers, the coaster, to move in a circle, all these forces are downward. So this will be the first part of the question. Second says, what provides this force? Remember, we said F centripetal, it is the subject. And then because these two forces are both downward here, so we'll say Fg plus F normal. Once again, that is because the passengers are upside down. If the passengers were above the track, remember F normal would have been up then, because we would have said Fg minus F normal, but luckily that is not the case at this point here. That is the equation. I think we answered these questions or questions like this, so you could just go through them. These are just repeated, and these are nothing new here. These are the summary of this one. There are perhaps maybe a few more questions I would like to answer, and then of course we're going to end up this question with. These are standardized test preparation. Remember the keyword I told you the other time. Whenever it says a circle, we can say there's always AC, there's always FC as well. Remember this too at this point here. Whenever it says constant speed, that means V initial, it is equal to V final. So we can say tangential is 0, tangential acceleration. And because it is angular constant speed, we can also say omega initial, it is the same as omega final. So even angular acceleration is 0. Okay, so remember this. It says, which one of the following is not true of the object? It is centripetal acceleration points toward the center of a circle. That is true, of course, because there is centripetal acceleration pointing towards. It is tangential speed is constant. Remember, it says speed, so yes, that is also true. C says it is velocity is constant. Is that true? No. Remember this, because the direction of the motion continuously changes, so the velocity is not constant. So this is incorrect. What about D says a centripetal force act on the object? That is also true because we have a circle, or you can say circular motion. All right. Now this one, I believe it is easy. These are nothing much. What is the most direct cause of the car's centripetal acceleration? That is obvious too. Car's direct centripetal acceleration, the rectilinear motion of the car. Rectilinear means the motion, or like the basically rectilinear motion. That would be motion in a straight line. Rectilinear. That's what it means here. The motion of a car with a constant velocity? No. Remember, in order to have centripetal acceleration, the direction of the velocity must change, so it cannot be constant. The force of the friction between the tires on the road, this one also causes actually the, like for example, if we have force of friction, which is directed towards the center, that causes the centripetal acceleration here as well. So that would be C, the normal force between the tire and the road. That is incorrect. And of course, this one is easy. We've solved questions like this. I believe you can solve this one on your own here. Now, what about 5 here? It says, which of the following is correct interpretation of this expression here? G, gravitational freefall acceleration, says G, or you can say this one, it is equal to capital G, constant of universal gravity, gravitation, mass of the Earth divided by the radius of the Earth. Okay, that's been very recent too, actually. So which one of these is correct? It says gravitational field strength changes with the object's distance. That is true, of course. The closer, the stronger, the further, the weaker the gravitational field strength. So this is true. All right, it says which of them is correct. So this one correct, but always go through the other options too. All right, it says free fall acceleration changes with an object's distance. Free fall acceleration, is it changing with the object's distance? Yeah, so that means even this one is true. So clearly now, if 2 options are correct, this must be all of them, or maybe double check your work. Free fall acceleration is independent of the object's mass. That is also true because we said this one comes from Fg, which is equal to mg, and then equal to mass times this much. So let's say the mass, both sides cancel out, so it does not depend on the object's mass. So in that case, of course, we can say all of the above are correct interpretations. That's a good one here. Now, as for question number 6 says, what data do you need to calculate the orbital speed? Do you remember the orbital speed? We said tangential orbital, that is equal to the radical of G capital, and then it was mass of the planet, and then it was radius of the planet. Remember, it was just radius, not squared. So based on this equation, remember what it depends on. It depends on the mass of the planet, the radius of the planet here. So it says the mass of the satellite, that is not the planet, which is the mass of the small object, that is incorrect. Mass of the planet true, radius of the planet true, but this one is not true. It says the mass of the satellite, once again, that is incorrect. The mass of the satellite, again, that is incorrect. You don't have to even read the continuation of this. Mass of the planet and radius of the planet only. I like this option, and that is the correct one here. All right. This one is also a very good one, actually. It says, which of the following choices correctly describes the orbital relation between Earth and the Sun? Watch this. It says the Sun orbits the Earth in a perfect circle. Is it the Sun that orbits the Earth? No. Earth orbits the Sun in a perfect circle. So nobody's perfect, right? So that is also incorrect, remember. C says the Sun orbits the Earth in an ellipse. Ellipse, basically here, that means an elliptical orbit. That's what it means here. With Earth on its focus here. Once again, is it the Sun that orbiting the Earth? That's no. All right, so again, this one is incorrect. Option D says Earth orbits the Sun in an ellipse with the Sun at, let's say, one focus. So this is correct because that would be the Earth here, right? And this is the Sun, this is ellipse, and the Sun is at the focus. So option D would be the correct one. All right, 8 says what? It says, which of the following statement is correct? Now, at this point, I believe I need to give you an explanation regarding the mass and weight. Mass is the amount of matter in an object. Imagine you have a basket. It has, let's say, 10, footballs, or let's say tennis balls. Now, the more tennis balls you add to the basket, the heavier it becomes. That is exactly what the mass is. The amount of matter in an object. Your mass would be how many particles, atoms, and molecules make you as a person here. That would be your mass. And no matter where you go, to the top of a mountain, to the bottom of a well, or even on the moon, let's say, how many particles make you, yourself, does never change, or does not change at this point. So we'll say mass will never change, because that is the amount of particle in an object. On the other hand, weight is the gravitational pull on our body, let's say, or the gravitational pull on an object. So we know that because gravitational force changes or pull changes, so weight will change by changing the location. We say weight varies by changing the location here. Okay, that depends on, we can say, the mass of the planet, the radius of the planet. So now, which one of these do you think it would be correct? It says mass and weight are both vary. Vary means change with location. That is incorrect because mass never changes. Again, mass changes with location. That is again incorrect. Weight changes with location, but mass doesn't. This one is correct. Neither mass nor weight varies. Neither mass nor mass change. That is incorrect because the weight does change. Last question that we have says, which astronomer discovered that planets travel in an elliptical rather than circular orbits? Now here we can say Johannes Kepler here. Johannes, let's say Kepler, that was the name of the scientist. Sometimes we pronounce it as Johannes Kepler, but the correct, that is okay, I believe, even though the correct pronunciation is Johannes Kepler, you could say. And then the scientist Nicholas Copernicus, that is not. You could say Tycho Brahe or Brahe, whatever it is, that is also incorrect. Claudius Ptolemy, that is also incorrect. So it is Johannes Kepler, you can say. That is the correct scientist here. Now, there's not enough actually. So we're basically done with this section, but you basically are not done with this section because there are a lot of Wuzari questions of, like for example, you can practice now whether this on this malzama or booklet, or it could be on any other malzamas. I hope you understood all the concepts, but now the real work begins at this point. You have to keep practicing and see how well you understood these concepts. If you do or solve the Wuzari questions, and if you, for example, solve, let's say 9 out of 10 questions every single time, that means you're doing very well. If you get 10 out of 10, that is perfect. Congratulations, keep it up. But if you're solving, let's say, sort of like 4 or 5 questions out of 10 Wuzari questions, then that means you did not master all the concepts. Go back and review one more time, go through the concepts, and then make sure that you understand them well enough, then you can get back to practice those Wuzari questions. Inshallah, next time we're going to start with the second chapter. that is basically an interesting one, and I hope you stay with us. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.